So let's do it. So suppose now I have a solution. I'm going to draw another beaker here. You would think by now I've gotten good at drawing beakers, but I haven't. Or that I would have drawn myself a beaker using PowerPoint. In any event, we've got liquid of A and liquid of B. We're mixing them together, right? And we note that they are in equilibrium with their vapors, each respectively in equilibrium with their vapors, okay? And let's also suppose that A is more volatile. And so what that means, it doesn't mean that it's more reactive. It means that the vapor pressure of pure A is greater than the vapor pressure of pure B, which you can actually see on this diagram right here. Okay, so if you notice, we've got another mole fraction diagram going on. Mole fraction of A at 0, mole fraction of A at 1. So when the mole fraction of A is 1, that means the solution is pure A. And you can see here, right, the vapor pressure pure A is greater than pure B. Okay. So now we have this other concept here. We've got an X or a chi, a Y, and a Z. Okay. So in these diagrams, Z is the generic mole fraction. Okay. Chi or X is specific for the liquid. So it's the mole fraction of the liquid. And Y is the mole fraction of the vapor. So on this axis, it's just an axis from 0 to 1. So that's why it's given Z. Z is just generic for mole fraction. But we also notice that we have here the mole fraction of A in the liquid. And we have the mole fraction of A in the vapor. Okay? So here is how, so in other words, YA is really going to be the vapor pressure of pure A divided by the total pressure at any point along this line, the total pressure of the solution. And of course, YB is the vapor pressure of pure B divided by the total vapor pressure. Okay? So now the way this works, so suppose I make a solution of mole fraction A. So suppose I make a solution of A and B with the mole fraction, whatever it is, right, at chi A, indicated by this point right here, all right? So these binary vapor diagrams, all right, the top line is always the liquid and the bottom line is always the vapor. So in other words, this blue line is the determination of YA, okay? And the red line is the determination of chi A. And we note that if both of these had the same vapor pressure, if P vape A was exactly the same as the vapor pressure of B, there would be no difference. However, because A is more volatile than B, it has an enriched concentration in the vapor. So in other words, if this is now my liquid mixture, where I've actually mixed these together, and that's the composition that I want, the concentration of A in the vapor, I have to travel straight across this constant pressure line, okay? And now that gives me my concentration of A in the vapor. And it will always be true that the more volatile component, in other words, the component that has the larger vapor pressure, will have a larger concentration in the vapor. Hopefully that makes sense, okay? And so what we would see here, so I'm going to write down an equation. I'm not going to hold you responsible for this derivation or anything like that. But the equation, this line, this blue line right here, is the following. So it goes chi A, so the mole fraction in the liquid, times the pure vapor pressure of A, divided by the pure vapor pressure of B plus the difference between the vapor pressure of A minus the vapor pressure of B times chi A. And then, of course, we could say YB simply just equals 1 minus YA, right? Okay. So now what we've got going on here, this is an illustration of the ratio of these vapor pressures. Okay. So for example, this line right here that says number 1, so this is actually PA divided by PB equals 1. And so again, as you can see, there would be no difference between the vapor lines or the liquid lines. Okay. But now look, if that ratio is 2, so if A is twice as volatile, now you start giving this curvature. And I'm going to put a different color line here to indicate what the liquid composition would be. Oops, let's see, I want a different color. So again, on this graph, okay, actually, yes, let's go back. Black. So on this graph here, this is the vapor. So all of these lines are the vapors, okay? And the liquid line is not drawn on here, but I can draw it because it's just a straight line connecting this point to that point, okay? So that would be the liquid composition if A were twice as volatile as B. And of course, if A were 4 times as volatile as B, it's going to look something like that. And so as you can see, what you get here, okay, what I'm going to refer to as a tie line, right? The lines that may be at one pressure connected to this pressure, that's called a tie line. And so let me draw that a little bit better here. Yes, so I've got a nice zoom in. So suppose I were to zoom in, where now here is my liquid line, okay, and here is my vapor line. Oops, let me draw that better. So I'm kind of exaggerating this. You know, I'm not showing these connected or anything like that. And so let's see here, vapor for this line, okay? So there exists some point that's halfway between these points, and that makes what we call a tie line, okay? All right? And what that tie line gives us here is if I go all the way down to where my mole fraction scale is, right? So this would be like, you know, I'm just going to say generic mole fraction, ZA, okay? We recognize that this line right here would be the mole fraction of A in the vapor, and this line right here would be the mole fraction of A in the liquid. And so what is that tie line? Okay, so this is now what we call the lever rule. And so I'm going to put a couple things down here, all right? So I'm going to write NL, meaning the number of moles in the liquid is on this side, and the number of moles of gas is on that side, okay? And we can actually then determine if, let's suppose, we had this composition, you know, where here is my liquid composition, here is my vapor composition. Using this lever rule, I can actually calculate how many moles are in the gas and how many moles are in the liquid by the following. We recognize the total number of moles is just going to be the number of moles of liquid plus the number of moles of gas. So that's the total number of moles I put in the solution in the first place. Okay? And so now I can say in total times ZA, so this point that's halfway between, equals NL times chi A plus NG times YA. Okay? And so what I can do then is some algebra. And I'm not gonna show all of this algebra, but basically it works out to be a proportion where now the length of this line, so I'm going to say LL and LG, is directly proportional to the number of moles. So the lever rule just simply distills to NL times LL equals NG times LG. So it's basically a proportionality. So if I scan across this graph, right, if I find a point that's halfway between my liquid line and my vapor line, and do these subtractions and do this proportion, assuming that I knew what the total number of moles was, which I would have had to because I made the solution, then I could actually calculate exactly how many moles of this thing are in the gas and how many moles of this thing are in the liquid. Okay, so that's all I'm really going to say about that on these vapor pressure diagrams. So be able to interpret these diagrams, understand the liquid line is going to make just a straight line from one vapor pressure to the other, and the vapor lines are going to be the one that's curved underneath. Okay?